Hello everyone. In third semester you have the course on modern physics, and I will be teaching you the first chapter on radiation and its nature. The first chapter basically talks about the transition from classical physics to quantum physics. But before we start the first chapter on radiation, let us know what is modern physics. So this is based on the post-Newtonian concept which began in the year 1890 with the discovery of Maxwell's concept. So modern physics is based on two major breakthroughs. One is the quantum mechanics and other one is the theory of relativity. So this course is all about how new ideas developed with time. Now the question is that even though classical physics was quite developed at that time and it was serving all the purposes, but still that transition was needed at that time from classical ground to the quantum ground. So the classical physics is a study of macroscopic system, whereas the quantum mechanics, which is believed to be the most fundamental theory now, is a study of microscopic system. So you see there is the length scale difference, and that length scale difference got reflected in the theoretical and experimental comparison. And because of that the paradoxes came out, and those paradoxes led to further studies. So as a result many pre-classical physics notions were overthrown with time. Now before we move into the topic, let us ask, what is light? Is it a wave, it's a particle, or both? Okay, so let us try to visualize. Drop a stone in a pond or lake or any water reservoir, and this is what we are going to see. Well, I'm sure all of you must have the experience of this kind of situation in your childhood. Okay, so drop a stone in a pond or lake, and what happens that the ripples, they form at the center, and then they move out away from the center. Okay, now if the two stones are dropped in two different places, let's say a meter gap away, the ripples, they form at two different sources, and then they spread out from the center, and then they cross each other but without affecting each other, and there is no backflow of ripples or anything like that. And same is for the two light sources, and this is the reason why people can use their mobile phones at the same time, but no disturbances during the calls. Okay, so that proves that the light is a wave. Now on the other hand, light obeys the laws of reflection, refraction, like particles. The particle-like behavior strongly revealed by the photoelectric effect, and we'll talk about the photoelectric effect in my next lecture. Okay, so here what happens is that when light incidents on a metal, it knocks out the electrons, and which is the evidence of particle-like behavior of light. So we see that in classical ground there are two independent disciplines. One is the mechanics of particles, and another one is the optics of wave. Okay, so now let us look back and see how the concepts evolved with time. In 1801, Young performed the double slit experiment. He observed the interference of lights and obtained the intensity with the help of superposition principle of light. So you can see here that the two secondary sources have been formed from a single source in order to maintain the coherence features. So here what happens that the interference due to the interference, a series of constructive and destructive fringes are formed on the screen, and this is possible only if light is a wave. Now if light is a wave, then what is waving? Normally any disturbance that propagates like a wave through a medium, but for light, what it is then? Okay, see, so in 1845 Faraday performed an experiment, and he noticed that the plane of polarization of incident light changed due to the applied magnetic field, and with this result he comes to a conclusion that light must be related to the electric and magnetic field. Okay, so the next surprise was in 1860 when Maxwell found that the electric and magnetic field are related to each other even in free space. So he developed mathematical relations to show that the changing electric field with time is accompanied by the magnetic field or the other way around, and this set of equations are called the Maxwell's equations. And then later in 1888 Maxwell's equations were verified by Hertz. Okay, so now all settled, and it was known that the light is an electromagnetic wave, and we had the answer for this question, which is that the accelerated electric charge that produces electric and magnetic disturbance, and that travels through the space. As you see, you can see here in the picture that this is the direction of electric field and this is the direction of magnetic field, and this is the direction or propagation of that disturbance. So then the question was, what was the next? So the next search was on radiation. Normally we notice any object when incident light gets reflected by that object, and also we see an object when it radiates or emits. So when radiation is related to the temperature, it is called the thermal radiation. And when a body is hotter than its surroundings, that is when a body finds itself hotter than the surroundings, then it cools off and comes to an equilibrium situation, and in equilibrium situation the rate of absorption of light is same as the rate of emission of light. We all have seen that when an iron rod is heated, it turns to red, then yellow, then to blue, white as the temperature is increased. So we see that the red, yellow and the white, which are the visible spectrums. However, it does not mean that the other infrared spectrums are absent. They are present as well, and but the human eyes, they cannot perceive those wavelengths. So in our day-to-day life, all macroscopic objects radiate or absorb at all temperature, and all thermal radiations can be approximated as blackbody radiation. However, perfect blackbody is a body which absorbs all the wavelengths regardless of the frequencies and the angle of incidence of light. An example of a perfect blackbody is the lamp black or the Bismuth black, which absorbs 98% of the incident radiation. Well, the name black is given because it does not reflect any light. Every frequency is absorbed by the black body, and that is why the name black is justified. And it is found that all black bodies at a particular temperature emit same spectrum, and this universal property makes them special and draw special attention for details for detailed studies. Okay, so in a lab one can mimic a black body by considering a hollow object with a small hole in it, as you can see here in this picture. So now if light enters into the hole, it gets trapped inside the cavity due to multiple reflections on the cavity walls. Therefore, the light eventually gets absorbed by the cavity walls, and it has been tested that the radiation which emits by this small hole has the property of Blackbody radiation. Therefore, the hole acts as an absorber as well as an emitter. So it is convenient to study the cavity radiation in order to apply very simple and general arguments. Now, how to study the radiation inside a cavity? So the radiation inside a cavity is considered to be a series of standing electromagnetic waves, and the nodes of the vibrations are on the walls. Now this can be mapped to a situation where, let's say, a number of strings are attached to the walls, then the strings are plucked, and as a result a series of standing waves are formed inside the cavity. Well, this mapping is possible because the light is considered to be a collection of photons, and each photon is considered to be a harmonic oscillator. So here in the picture you can see a series of standing waves of different wavelengths, such as 2L, L and 2L by 3 and so on, and can be written in the following general form, which is lambda equals to 2L by J, where J is the quantum number, and that determines the energy levels of the vibrations. As the light velocity, which is c, is related to the wavelength lambda and the frequency nu, so then the quantum number J can be represented in the following with this following form, which is 2L by c into nu. So in 3D you can see the J has three components: Jx, Jy and Jz. So the number of standing waves can be found as here you can see this is Gj dj equals to 2 into 1 by 8 into 4 pi j square dj, where j is the count of the number of nodes along the j axis within the range j to j plus dj, and that essentially measures the energy. So we see that there are two different factors in the expression, which is 2 and 1 by 8. So this 2 is for the two different direction of polarization, and 1 by 8 is to represent one quadrant out of 8 quadrants. So because you see that the cavity walls are at 0 and L. So in 3D, if a cube is considered, then one corner of a cube is at the origin. Hence the contribution will be from one quadrant only. Okay. So the number of standing waves in terms of the frequency can be written in this following form, which is G nu d nu equals to 8 pi L cube nu square d nu by C cube. So here you can see there is a volume term here on the right hand side. So now if we just simply divide this expression on both sides by L cube, then we are going to get the number density per unit volume, which is G nu d nu equals to 8 pi nu square d nu by C cube. And you can see that this G nu d nu is independent of the shape of the cavity. Therefore the blackbody radiation or absorption does not care about the shape of the cavity. So now in equilibrium condition, each standing wave corresponds to average energy, which is the kinetic energy plus potential energy equals to kT at temperature T, where K is the Boltzmann factor. Therefore the energy U nu and d nu can be written in this following form, and this formula was derived by Rayleigh-Jeans. So this formula is called the Rayleigh-Jeans formula. Now the question is that do you think this formula is correct? So let us verify it. Okay, so let us plot the number density or the energy density as a function of frequency. So you can see here that in this plot, which is the Rayleigh-Jeans curve, as nu increases, energy density also increases. So as nu tends to infinity, energy density also goes to infinity, and which is not possible, obviously. And you can see the other plot which was observed experimentally at temperature 4000 Kelvin. So we see that there is the discrepancy, and this discrepancy is known as the ultraviolet catastrophe of classical physics. And this led Planck to think further, and as a result the quantum mechanics takes an entry. So then he proposed a formula, and the average energy kT got replaced by this term, which is h nu by e to the power h nu by kT minus 1, and here h is called the Planck's constant, and then the value of h is 6.626 into 10 to the power minus 34 joule second. Okay, so Planck actually later on told that it was his guesswork. In fact, if you feed the observed data, you can find such function. Okay, so now let us check how good this modified formula is. So as there is the exponential term, so there can be two limits. So in one limit, when h nu is much greater than kT, that is when frequency is much larger, this exponential term that diverges, and as a result this u nu du nu will be 0. So you can see that there is no ultra catastrophe. Okay, so and then in the next limit, when h nu is much less than kT, then the exponential term can be expanded in a series, which is the Taylor series, and then we are going to get the Rayleigh-Jeans formula back, which is this 8 pi by cq into nu square d nu. So now if we plot this energy density, we get these plots for various temperatures. So this is a plot of the energy density as a function of frequency. I'm sorry, it's not visible here. Okay, so if we now integrate this formula, the expression on both sides, where nu goes from 0 to infinity, then the energy density will be a function of temperature, which is T to the power 4, and this is known as this formula is known as the Stephen-Boltzmann law. Okay, so in the picture what we notice is that as we increase the temperature, the peaks of the plots move to the higher frequency region. That is the wavelength that is decreased. In fact, in our day-to-day life, we also see the same situation, that when the temperature of the object is small, then we see the larger wavelengths, for example the red, and as we increase the temperature, the wavelengths becomes the smaller, that is the frequency becomes higher, and we go to the infrared region, and which we cannot see with our bare senses. Okay, so now it is interesting to look is that if we simply take the ratio, which is this T, where the peak is forming. So if we take the ratio T by let's say nu max, where the peak is formed, then it comes out to be constant, and this is called Wien's displacement law. In fact, the same mechanism is used to prepare the device, which is called the pyrometer. In fact, in this present situation, in this COVID situation, everywhere the thermal gun is used, and in that thermal gun the same mechanism has been used to measure the body temperature. In fact, by looking at the stars, by looking at the wavelengths of the star, I mean the color of the star, we can also estimate the temperature of the star which are far away from us. Now let us try to understand the physics behind Planck's newly proposed formula. So one of the fundamental properties of quantum mechanics is Planck's postulate. So the postulate is the following, that the energy of oscillators or standing waves in a black body is quantized in the following manner. So the energy is given by NH nu, where n is the positive quantum number which goes from 0 to infinity. So each packet with energy h nu is called quanta for a particular frequency nu, and we see that the energy gap between two consecutive energy states is h nu. So if a particle jumps from the state, let's say excited state, to the ground state, then it has to radiate, whereas if a particle jumps from ground state to excited state, it has to gain energy h nu. So during this process, this simulated emission or absorption and spontaneous emission take place. So now if in the equilibrium situation, if the rate of absorption and rate of emission we set equal, then from the statistical probability, the modified average energy proposed by Planck is justified. In fact, we can understand this new average energy if we try to understand the Boltzmann statistics. Okay, so let us have a system of 4 particles of same type at temperature T, and if we arrange these 4 particles in such a way that the total energy is 3 delta epsilon all the time for every distribution. For example, in this first distribution, let's say there are 3 particles with energy 0 and 1 particle with 3 delta epsilon. Then in all total the energy is 3 delta epsilon. For the second distribution, 2 particles with 0 energy, 1 particle with delta epsilon, 1 more particle with 2 delta epsilon energy. Then the total energy is 3 delta epsilon, and so on. So now we see that in the first case, as the balls are of different colors, so the total number of ways to arrange them would be 4, and similarly for the second case, the total number of number of way we can arrange these particles is 12, and so on. So now if we add all these numbers, total number of ways to arrange the 4 particles would be 20, like 4 plus 12 plus 4, that is 20. So now we can write down the probabilities, and they are the following, which is 4 by 20 for the first case. For the second distribution is 12 by 20, and so on. So after all these, now if I try to calculate the number of entity, let's say with energy 0 or delta epsilon or 2 delta epsilon and so on, then in the first case with energy it comes out to be 40 by 20. So how do we get this? So there are 3 particles and with probability 4 by 20, so I will multiply this 3 into 4 by 20 plus 2 particles with this probability, so 2 into 12 by 20, and in this third case we have only one particle with zero energy with probability 4 by 20, so 1 into 4 by 20. So if we add all this, then the probability, so the number of entity we are going to get is 40 by 20. Similarly, for the second energy distribution, which comes out to be 24 by 20, for this case 12 by 20, and so on. So now if we simply fit this data, in fact you can try at your home in your computer, and you will find that the function will come as will come in exponential form with two fitting parameters, and which is the function will be in this form, which is e to the power minus epsilon by kt divided by kt, where epsilon is the h nu. So this is the probability function in terms of energy, as you can see. So now once we know the probability, we know everything, so we can find the average energy out of that. And now we see that that Planck's radiation formula is in exact agreement with this formula. In fact, because of that, now we see that the radiation formula is in exact agreement with the experimental observation. Okay, so we see that the whole story turns into a new story, and that was only possible because of age. So age did the miracle. Okay, so we see that it's not that the classical physics was wrong, only that we could not realize with our bare senses. For example, so these are the classical energy levels and are continuous from 0 to infinity, whereas these are the quantum energy levels and are discretized. You can see the energy levels are 0, h nu, 2 h nu, and so on. And this is possible because the smallness of h makes the energy too fine, that is why we can distinguish different energy levels in quantum mechanics. I mean, just try to see a tree from far and then go to go nearby, and then you will see that the differences are that from far you can see the envelope of the tree, whereas if you approach the tree, if you go nearby the tree, you will see the detailed structure of the tree, for example the leaves, the trunk, and branches, and so on. So we could see the detailed structure in quantum mechanics because we have the weapon, which is h, in our hand, and with this weapon the